Okay, I noticed that my cute little picture down here is like lags far behind real time, so I don't know if that's really good to have there or not. But at any rate, let's look at, we'll go to projector mode here. Let's look at graphically, so this is kind of LP graphs part 2. So I have a simple objective function, z equals x plus y. Now, you actually, with Desmos, I had to write it this way. If I tried writing z equals x plus y instead of x plus y equals z, it doesn't work. Desmos, assumes certain things. It likes x and y. So, if I said x1, x2, it would have problems. So pretty much it likes the x being the x-axis down here and the y being the y-axis, and so we have that. But z is a slider, so as I slide it, we see that we get all these this family of parallel lines, and so I'll put it down there to begin with, and then we have constraints. Now this actually came from a problem that had to do with some sort of I think fertilizer, feather, fish, kelp, and sphagnum moss, I think, or something like that. It was a mixing problem, and you have some mixing problems. So here are the constraints, and I'll add them. I've already put them in, but I'll add these one at a time. And notice I just put them in as less than or equal to. Well, what is that? So if I click on that, that is everything below this line up here. And so the top is the line, 0.1x plus 0.4y equals 50, and I have that down here. So if I do that, right, there is the line, but then everything less than or equal to that heads toward the origin, and so I'm going to turn that off for now. And then we have these other constraints, and what happens? Well, every one of them is what we call a half plane, okay, because it'll be one side of a line. And so this is one side of the line, so it's half the plane. And so click on that, and we get this other. Click on that. Click on that one, that they have to be less than or equal to 30. Now, we also typically would have the positivity constraints that x had to be greater than or equal to 0 and y had to be greater than or equal to 0. But in this case, we actually have x has to be greater than or equal to 20, and y has to be greater than or equal to 15. That's interesting. I just looked here, and that's not, this is something else, so we'll have to fix that up, but that's okay. So click on that, and click on that, and wow, that's pretty much impossible to read. Now, I can just hit, all the equalities here, and then if I know which direction the inequalities are going, what I realize is I have this space in here that suffices for all the constraints. All the less than or equal to constraints were these 4 lines up here, and they were all on the 0, 0 or origin side of it. But then we had x was greater than or equal to 20, so that put x here and farther out that way, and y greater than or equal to 15, so y had to be here and then up that way. So I can see it a little better that way, and I can leave those up. But what we can do in Desmos is just to kind of show this region. Desmos limits things basically as ands. So it looks at these inequalities as ands. If I string them together, with these curly braces around them. And if here you see, what I did was I listed one of these constraints. This very first one, I listed it as the constraint, and then these others are all within the curly braces. Now, I'm not sure, I copied this from something else I had done for another class one time. So my guess is this was a change. We changed the requirement here. And so what I'm going to do is put that, I guess the x has to be greater than or equal to 20. So I'm just going to change that to 20, like that. And the y has to be greater than or equal to 15. So I'll put that in there. And you see now I have every one of those constraints in a single line. And again, one of them had to be not in the curly braces to make Desmos do this right. But what it did was it said, well, all of these things have to be true, so an and statement. So each constraint has to work, and it looks at the intersection of that. And so first I will turn off all these, and so I can see a lot better. And then I will turn this one on, and there you go. So there is the region that is common to all the constraints. And so if this region were empty, in other words, if I had said x had to be greater than or equal to, I don't know, it looks like my face is in the way here. I hate it when that happens. But that looks to be about 200 down here. And so if I said x had to be at least 200, well, we see that actually I would have no feasible region at all. This would be an infeasible problem or an infeasible model. But with this, we do have an intersection that's non-empty. And so any points in here will work. They will satisfy all these things. I'm not going to go through and check them all and so forth, but here's a x is 100 and y is 50, and so if I well, I thought I could click on that and get that point to show up. I guess I can't. But certainly x of 100 is bigger than 20, y of 50 is bigger than 15, so those two work. And then we could check out each of these others. We'd get 10 from here and 20 from there. 10 plus 20 is 30, so we're less than 50 and so forth. Okay, so that we have that feasible region, and now I can come up here and try different values of z just by sliding this, and you see I cannot actually get a value of 20 because x plus y equal 20 doesn't intersect this region. There are no xy pairs that will satisfy all the constraints. And so I move it up, and at this, it's kind of hard, right in there somewhere. Maybe that's it. I can try bringing it down here, 37, 36, 35. It looks like 35 is the smallest I could get and satisfy all my constraints, and you see that is right there at x equal 20 and y equal 15. And let's see if I can click on that one. Oh yeah, there we go. See, 20 and 15, so that one I could click on, and probably as I move this up through here I can click on it. But there's a case where if I chose x equal 20, y equal 15, I could make this thing be 35. However, I can slide z up, I can get to 110, And I have lots of points that will work for 110. That works. That works, right? Any of these points work, and they'll add to 100. Feasible. I can do better than that. I can do more. And notice, if I just keep moving it out, I can get to, well, not very good at going, so we'll have to move it out little by little. But I'm getting out toward this point right here, so that appears to be the answer I want, right? Somewhere in there, 170.588, and so I can try 245 here. That's not quite far enough. Right, I'll make that bigger, and you can see that it's not quite there. How about 246? I don't think it's quite there. 247. And I think, yeah, it looks like, see, there's an intersection of that blue line, the objective function, and this. And now I can zoom in to check to make sure, is it really a single two, and add 2, I can make it a little bigger yet if I zoom in. And, so this would be like, 0.1, oh, too much, 0.03. And, in the end, what can I do? Well, I can just click here and look at that intersection of 170.58 and 176.471, and that intersection gives me, and I'll try to sort of add these in my head. What do we have? 76. That's 246. But then these two numbers together do make more than 247. What do I have there? I've got a 9 in the third decimal spot. I have a 5 here, and then a 0. So 059 is what it looks like. And so if I go to this thing and do 059 and click that, then as I zoom in, it does appear that there is a single intersecting point there. Okay, so about 247. And I can zoom back out. For that was from looking at this polygon here, a convex polygon, is if I take a point there and take a point over here and draw a line between them, I'm always inside the figure. Then as I move that line out, I always hit a corner. If I was minimizing instead, well, I would move that line towards 0, and again I would hit a corner at some point. And if I change my objective function to be, say, 2x, then you see I have that, and well, I'd have to slide this thing out, but it looks like I might hit this spot here instead. Take this all the way to 300. That's not big enough. Let's go to 500. That is big enough. And so now I'll scoot it back, and as I bring it in there, yeah, it looks like it's going to hit that corner as opposed to this corner or that corner, and so I could bring it in and get the answer that way. So we'll take it back to just an X, and we were right around 247, so I'll just put that in. And we see that we're about there. And let's see, so anything else we needed to mention? Let me think here. So that was our objective function. If I changed changed the objective function a little bit, it changed the slope, and I got a different answer. And I think that's what we wanted to point out for the graphical situation. Again, we are always going to get this nice polygon, a convex polygon, unless it's empty. And then, of course, another possibility would be that if I got rid of all those other constraints, if I got rid of those, I'm not going to, well, I can get rid of the shaded area. Well, if I only insist that x be greater than 20 and y be greater than or equal to 15, oh, well, an unbounded, I guess, maybe. I'd have to think about that. This could grow without bounds. We could have an infinite, or we could have unbounded region. Either one could happen. And in this case, though, we had our bounded, non-empty feasible region. So that is the graphical idea, and so again, it seems reasonable that we ought to be able to find that answer, and a decent algorithm that works well in practice is the simplex algorithm. And what that does is it pretty much it starts here at 0, 0 and then starts going around the polygon to check the points. And so it's possible that one direction might be quicker than another, but usually we can't. We don't know that that's happening in our work. But that in 2 dimensions is an analog to what happens in many dimensions, and so we'll call that LP Graphics Part 2. And somewhere I'll finish it. There we go.